This is going through the answers to the pedigree worksheet you had. So we talked about the first one together, but I'll go through it again. You're going to read what it says. It's telling you that straight thumb is a recessive trait and that hitchhiker's thumb is a dominant trait. It's telling you that the two shaded in people on here have straight thumb. So in order to have straight thumb, you have to have, these are the straight thumbs here. It says it's recessive, so the only way for these two to be straight thumbed is they have to have the recessive traits. They have to look like this. Well, let's use an H since it's hitchhiker. We'll use lowercase h's. That's what they look like. So we know one is lowercase, homozygous, recessive, homozygous, recessive. Now we're going to look at 3 and 1 right here. It's asking what is the genotype of this person. This is a parent of these. The only way for them to get it, if this parent had it, they would look just like that. So they don't, so they have to look like this, just as this parent does in order to have children of this genotype. So 3-1 is heterozygous. 3-2 is heterozygous. Then what is the genotype for 2-3? This person right here. This is the parents of this one who's heterozygous. These guys are normal as well. All are normal. So in order for us not to have any of them have it, but this one does, we know that one of the parents has to be a carrier and the other parent is probably normal, right? Because none of these have the trait. So if I did a Punnett square and I said dad was heterozygous and mom was homozygous dominant, it would show me that most of my kids would be normal, but they'd be carriers. So this person here is a carrier, along with this person here is a carrier, right? So I am saying he's a carrier and she's not because nobody else in the family from these parents have the trait. So this family that this daughter came from, which are these parents up here, are normal, and he's the one who brought into the family the hitchhiker thumb trait, or the straight thumb trait. The rest of them have hitchhiker's thumb, don't they? What type of genotype? We said that 3 had to be heterozygous as well. It says, is it possible for individual 4-2, this one right here, to be a carrier? Yeah, because both parents, again, if we do the Punnett square of the heterozygous parents, we have that they have a 50-50 chance, right, to be carriers. So, yes, they can be carriers. This one could be a carrier. And why? Because it's a 50% chance. Right? Okay. So going on to the second one, this one is sex-linked. Let me go back to my highlighter. This one is a recessive sex-linked. So we know that this, in order to have it, remember it's on the XY for a boy, XX for a girl. This is telling us they're a carrier. So what are we looking at? Color blindness. So we'll use a C. A capital C, a lowercase c would indicate a carrier for a girl. And for a boy, he has no way to get away from it. So he's going to have that little c that causes him to be colorblind. Same for all the rest, the boys and girls. So let's look and see what it says. What do the half shaded circles mean? It means they're carriers. What is the only sex carrier? Their carriers of colorblindness? That'd be female. which individuals are colorblind. They've got all the boys being colorblind. So we say I1, so we're to 3, right? 3, we have this one here and this one here, so 1, 2, 3, 4, and 5, 6, 7, 8 for this group here. Then on the bottom we have I4, 1, and 5 that have colorblindness. Which is the genotype for person 2, 2. Their genotype would be heterozygous because they're a carrier, but they don't have it. There's a genotype for person 1, 1. 1, 1. It's a boy, and he's colorblind. Oh, I'm sorry. Let me go backwards a second. Remember, this is on the sex linked, so this is a girl. She has the heterozygous. Then the boy has the lowercase c with the y, which makes him colorblind. I don't know if you can tell that's a lowercase c, so let me try again. They don't give me much space to work there. And 3, 3, 3, 1, 2, 3, this one right here, what's the genotype for that person? Remember, this is XX because it's a girl, right? And it would be, they're normal, so they have 2 capital C's, don't they? Those look like 2 capitals. Okay, if person 4, 1, this one right here, marries a female who's not colorblind and is not a carrier, what are the chances that the male offspring will be colorblind? Well, colorblindness is caused by mom. So if she's normal, she has the 2 capital C's, and he has 4, 1. He's colorblind, so we know that he has the lowercase c with his y. So you can do a Punnett square, which shows x, c, and y, x, c, and x, c. She doesn't have it. So what are chances male offspring will be colorblind? We said she's normal, so there'd be no chance the boys would be. Are there any females? Well, let's do the Punnett square to see. It's saying, will they be colorblind? Remember, these first 2 are going to be girls, these 2 are going to be boys. 50-50 for kids. So we know that the X, capital C, lowercase c, capital C, lowercase c, capital C, and capital C. So again, all of the boys will be normal, the chances of the boys, and then for the girls, they'll be carriers. So they won't be colorblind, but they'll be carriers. So none of these offspring will have it, but they can be carriers. Okay, last one is about sickle cell anemia. Sickle cell anemia is a recessive disorder. It's not sex-linked. So when we look at this, it says which number of the family above is affected by sickle cell. It'd be all the ones that are red. They're showing you over here. Sickle cell anemia would be fully colored in. So all these are the ones you're going to write down. I1, I2, 2, 3, and 7. I3 is 3. So then it says how many individuals in 3, 4, and 3, 5 are, how are they related? 3, 4, and 5. They're related because they're siblings. Brother, sister. Bro and sis. Right? How is individual 1, 1 and 1, 2 related? 1, 1 and 1, 2. They're related because they're married. How are individual 2, 7? Let me erase all my work up here so we can see what we're talking about. Oh, my eraser's not working. There it goes. Okay, so we're looking at 2, 7 and 3, 2. How are they related? Well, these are her parents. These are her grandparents. So this would be her uncle, aunt, aunt. So it's her aunt. How is 2, 7 and 2 aunt and niece, I guess. Right? How's individual 1, 2? Let's erase this. I just told you some of it. So let's see if they follow this time. So it's saying 1, 2 and 3, 5. It says, how are they related? Well, these are his parents and these are his grandparents. So that's his grandma. Okay, how do children 1, 1 and 1, 2 have? How many do they have? So let's look. Let's erase all my mess again. It's asking how many kids do these two have? They have, remember, it's only where they're attached. So 1, 2, 3, 4, 5, 6. They have 6 kids. How many girls did 2, 1 and 2, 2 have? 2, 1 and 2, 2. 2, 1 and 2, 2. How many children, or how many girls did they have? They had 2 girls. How many have sickle cell anemia? 1. Label the possible genotypes for individuals in the pedigree. One person having more than one possibility. So we only have one who has 2 phenotypes or genotypes. So let's label everybody. We know that to have sickle cell anemia is a recessive trait. So we would, I'm just going to pick, let's do B's. B, and B, right? This would be normal. This is a carrier. And this is have it. They have anemia, sickle cell anemia. Right? So we can go ahead and label because we know this one here has sickle cell anemia. This one, lowercase b's. That's just the letter I chose. It doesn't matter what letter you use as long as they're both lowercase letters. Okay, now we have to get to the harder part, which is to decide what is everybody. So in order for these kids here, any of these kids in this row here, these parents here, would have to be carriers. That's the only way to pass this on to this child here. So mom is heterozygous. She's a carrier. And the ones who aren't colored in are carriers because they carry the trait. If you want to do a Punnett square, you can see it. Let's see it. So this is dad. This is mom. So they are either going to have it or they're going to be carriers. And that's for all their children. So we have the ones that have it. Now we're labeling the ones who don't that are carriers. Okay. Now, oops, wait, I take that back. We've got to take these guys back. That one's right, that one's right, that one's right. This one we can take off. And this one we can take off because we don't know yet. We haven't decided yet. We've done the parents up here. We've done the children here. Now we got to go look at the husbands and then their children. So again, if we go back up here, it's the same situation with these two parents as it was these two up here. we know he has to be heterozygous because of the Punnett square we did at the bottom. So we also know that the children are going to be the same as their aunts and uncles, heterozygous. Now that leaves us with these guys right here in the middle. Now, they said one person will have more than one possible genotype, and that would be this guy right here, because we don't know if he's a carrier or if he's normal, because they didn't have any children with the disorder. So the children are going to be, hang on a second here, let's look. So if mom and dad, we don't know what dad is, right? So let's do our Punnett square over here. If we say he is homozygous, meaning he doesn't have it, and mom is heterozygous because she's a carrier because of her parents, we can look and see that they have a 50-50 chance of being normal and 50-50 chance of being a carrier. If we do the heterozygous parent with the heterozygous parent, we can have the option 25% chance that the children would be carriers, or I'm sorry, 50% chance they'd be carriers and 25% chance they'd have the disorder, and then 25% chance they'd be normal. So the likelihood they've had 2 children without any effect at all, we're going to see that they're either going to be a carrier or have the disorder. So these 2 kids would be heterozygous. I think we've labeled everybody. Looks good. All right. That's it. If you have any questions, please let me know.